You know, there's this really fascinating quote from the educational philosopher John Dewey. He basically said, "We only think when we are confronted with a problem."
Oh, yeah. It's a profound idea, really.
Yeah.
Especially when you think about how true intelligence isn't just, passively absorbing a textbook. It comes from actually bumping up against a challenge and having to figure a way around it.
Right, exactly.
Hmm.
And, well, Dewey was talking about human psychology, over a century ago, but we are pulling this exact philosophy into a completely different realm today.
Artificial intelligence.
Yep, artificial intelligence. Because today's deep dive is looking at a brand new foundation paper. It's called MCP-Zero, Active Tool Discovery for Autonomous LLM Agents. And it points out this glaring flaw in how we build AI right now.
It really does.
Yeah.
I mean, in our rush to make these systems super helpful, we're actually making them incredibly lazy,
Yeah, we are spoon-feeding them too many answers up front.
which is becoming a massive roadblock. If we actually want to move from an AI that just chats with you to a real autonomous agent that can execute complex multi-step workflows on your computer, we have to fundamentally rethink how it accesses information.
So our mission for this deep dive is to unpack exactly how this MCP-Zero framework is attempting to fix that roadblock.
Right.
We want to explore how we can shift AI from being this overwhelmed passive consumer of massive data dumps into an active autonomous problem solver.
And most importantly, we'll look at what this fundamental shift means for how you, the listener, will actually interact with your own digital assistants in the near future.
Exactly. So to really grasp the magnitude of this shift, we have to establish how large language models interact with the outside world right now.
Yeah, let's set the stage. On its own, an AI model is essentially a brilliant brain trapped in a jar.
I love that analogy.
I mean, it has all its parameters and training data, but it can't actually do anything on your laptop. It can't browse the web, it can't run a calculator, and it definitely can't read your files. Not unless developers explicitly hand it external tools.
Right. And the way developers hand it those tools right now is through this method called context-based tool injection.
Sounds very technical.
It does. But let's break down what that actually looks like under the hood.
Well, the foundation of this relies on something introduced back in 2024 called the Model Context Protocol, or MCP. It's an open standard that lets AI securely access tools via JSON RPC messages.
Okay, let's put a pin in that for just a second. Whenever we talk about JSON RPC, listeners should just think of it as like a universal translator for software.
That's a great way to put it.
It's just a standardized way for two completely different programs to talk to each other over a network. It lets an AI running on some massive server farm send a perfectly formatted instruction to your local laptop, say, to open a specific folder without needing a custom-built bridge for every single app.
Exactly. MCP totally solved the fragmentation problem. Suddenly, instead of building custom connectors, developers had hundreds of standardized MCP servers available. File systems, databases, specialized APIs, you name it.
But the problem isn't the tools themselves. It's how we introduce the AI to this incredible ecosystem, right?
Yeah, and that brings us back to context-based tool injection. It essentially means stuffing the AI system prompt with a giant instruction manual for every possible tool it might ever need.
It's wild. Before you even ask the AI a simple question, the system secretly shoves an entire catalog into its working memory. It says, hey, here are all 50 tools you possess. Here's the exact formatting required for each one, the parameters, the error codes, the edge cases.
All before you even type, hey, what's 2 plus 2?
Right, and that completely compromises the AI's autonomy.
It really does. When you inject these massive comprehensive tool schemas into the prompt, you force the agent into a purely passive role. It just scans predefined options rather than actively reasoning about what it needs to accomplish a goal.
You take this highly capable reasoning engine and basically turn it into a stressed-out database query system.
And a very expensive one at that.
Oh, definitely. I want to look at the sheer scale of this problem because the paper from the ArcSev 25 ERA 6.01056 gives some shocking numbers regarding token counts.
Yeah, the numbers are pretty staggering.
And before we dive into the math, whenever we mention tokens, listeners should just think of them as the basic building blocks of text that an AI has to process. A token is roughly a word or a piece of a word.
Right.
So the researchers point out that just the GitHub MCP server alone requires over 4,600 tokens just to explain its 26 tools to the AI.
And keep in mind, a real-world autonomous agent isn't just going to use one server.
Not at all. If you look at a comprehensive tool ecosystem today, it easily exceeds 248,000 tokens.
Wow.
Imagine going to a restaurant, sitting down, and before you can even order a glass of water, the waiter forces you to read the entire supply chain manifest. And the agricultural history of the tomatoes and the step-by-step recipes for every single dish on the menu, you would be cognitively exhausted before you even figured out what you wanted.
That is exactly what happens to the AI. The cognitive load, or the context window overhead, is paralyzing. It
Ugh.
slows the model down, it costs an absolute fortune in computing power, and it actually degrades the AI's reasoning ability.
Because the instructions just get lost in all that noise.
Exactly. So the industry tried to build a Band-Aid solution. It's called Retrieval Augmented Generation, or AIR.
Right, our art is everywhere right now.
It is. The idea is that instead of giving the AI all 248,000 tokens up front, a separate secondary system looks at your initial prompt, guesses which tools you might need, and only injects those specific tool manuals into the context window.
Wait, that actually sounds pretty logical. It attempts to act as a filter, right? It pre-selects tools based on your first message. So if I ask for code help, just give the AI the coding tools. Why doesn't that work?
Well, the researchers identified a couple of major flaws. The first one they call the static capability assumption.
Okay, what does that mean in plain English?
It means RAG relies on a query once, retrieve once paradigm. But user queries, in the real world, are broad and composite. You don't actually know what you'll need for step 4 of a complex task until you finish step 3.
Oh, I see. So if I ask the AI to build a website, it might need a coding tool first, but it won't know it needs a debugging tool until the code actually breaks.
You nailed it. Let's take an example directly from the paper. Imagine you ask the AI to write and run code to crawl AI repositories from GitHub.
Okay, so that requires multiple subtasks. It needs to write code, access the internet, and execute commands in a terminal.
Exactly. But a single round RAG retrieval might just look at your prompt, key in on the word code, and fetch a code writing tool.
Ah.
But it might completely miss the command execution tool needed to actually run the code. And because RAG only retrieves tools at the very beginning, if it fails to grab everything you need for the final steps, the whole task just dies.
The AI gets stuck and throws an error. That makes total sense.
And there's another major flaw the paper brings up with this RAG approach, which they call the semantic distribution gap.
Semantic distribution gap. That sounds like a translation problem.
That is essentially what it is. Think about how a human speaks versus how an API is documented. Your raw, casual user query, something like, debug this weird file, exists in a totally different semantic space than the highly formal documentation the retriever is searching through.
Right. The official documentation might be labeled something crazy like diagnostic error resolution via file path ingestion.
Exactly.
So it's like trying to match casual street slang with a dense legal dictionary. The keyword matching completely fails because the words don't look anything alike, even if the intent is exactly the same. The precision just drops off a cliff.
Which leads to a profound realization by the researchers. Because static retrieval fails when tasks evolve, the AI needs a mechanism to ask for tools during the task, not just at the beginning.
And that leads us directly to the core innovation of this paper, MCP-Zero.
Yes. This is the paradigm shift from passive to active.
MCP-Zero abandons the entire concept of handing the AI a menu up front.
Completely.
Yeah.
Instead, it restores what they call tool discovery autonomy to the language models themselves. The AI actively identifies its own capability gaps and requests specific tools on demand exactly when it needs them.
I really like this visual concept from the paper to explain this. Think of it like a robot eating a meal.
Okay, let's hear it.
Instead of giving the robot a massive, messy toolbox at the very start, the robot just sits down to eat. It realizes it needs to eat a salad, so it asks for a fork and gets it. Then it encounters a steak, realizes it needs to cut it, asks for a knife and gets it. Then it gets to the soup, asks for a spoon, and finishes the meal.
That's a perfect analogy. It's progressive task breakdown. But what's crucial is how the AI asks for these tools, which the paper outlines as the active tool request mechanism.
How does that work?
The model generates a structured request with two very specific fields, server and tool.
So the server being the platform or permission domain like GitHub or your local file system.
Right.
And the tool being the specific operation type like read file or search repository.
Exactly. By having the model generate these fields based on its own internal reasoning, rather than relying on the user's messy initial query, it creates perfect semantic alignment.
Because the AI is essentially speaking the exact same formal language as the tool documentation. It bridges that semantic gap we talked about earlier.
Yes, but this naturally introduces a massive engineering hurdle.
Right, I was actually going to push back on this exact point.
Go for it.
If the AI asks for a knife, how does the system find the right knife out of thousands of tools without reading the whole 248,000 token database. Isn't the AI constantly stopping to ask for tools going to add massive computational complexity? You're basically just trading context bloat for search delay.
It's a very fair concern.
Yeah.
But this is where the researchers introduced hierarchical semantic routing. It's a two-stage algorithm that fundamentally changes the math of the search process.
Okay, break that down for me.
Well, in computer science, we talk about time complexity. In a traditional passive system, if you have to search every single tool, we call that O of n complexity. It means the time it takes scales in a straight line with a number of items.
So if you have 10 times the tools, it takes 10 times as long.
Exactly. That is terrible for scaling. But the hierarchical routing breaks this down to avoid that linear trap. Stage 1 doesn't even look at the individual tools. It filters the candidate servers first.
Oh, I see. It just looks at the high-level server descriptions to find the right domain. It's like finding the right aisle in a massive hardware store. You don't look at every single screw in the building. You just navigate to the fasteners aisle first, and you ignore the plumbing and electrical sections completely.
That is a brilliant way to visualize it. That drastically narrows the search space immediately. And to make this even more accurate, they use AI-generated enhanced summaries of those servers to match against the AI's request.
Okay.
Then, in stage 2, it only ranks the specific tools within those pre-selected servers.
But wait, how does it actually match the AI's request to the tool descriptions? If we aren't using simple keyword matching, what is doing the heavy lifting here?
They use OpenAI embeddings, specifically the text embedding 3 large model.
Ah, okay. Let's do a quick deep dive into embeddings because it sounds like magic, but it's just really cool vector math.
It really is.
Imagine a giant, multidimensional mathematical map of human language. On this map, words aren't arranged alphabetically, they're plotted as coordinates based on their underlying meaning.
Right, so the casual phrase, squash this bug, and the highly formal API term, diagnostic error resolution, might look totally different in raw text. A keyword search would never connect them.
But on this mathematical map, their numerical coordinates are sitting right next to each other in the exact same neighborhood.
Exactly. The routing system turns the AI's request into one of these mathematical vectors and finds the tool description that is physically closest to it in that 3D space. It matches the intent, not the vocabulary.
It's incredibly elegant. Let's look at how this iterative active invocation actually plays out in action. The paper walks through a really cool debugging example, specifically a file called src/train.py.
Yeah, let's walk through it. So step 1. The AI receives the user's prompt to debug the train.py file. It assesses its current state and realizes, hey, I can't even see the file.
Right.
So it autonomously generates a request to the file system server for a read file tool. The embedding system finds it instantly, hands it to the AI, and the AI reads the code.
It actively acquired its first capability. Now, step 2. It reads the code, spots the bug, and realizes it needs to change the text.
But it doesn't have an editing tool yet.
Right, so it generates a new request for an edit file tool, it gets it, and modifies the code.
But here's where the reasoning really shines. Step 3. The AI fixes the bug, but then its logic kicks in and it decides, I should probably test this to make sure it actually works before telling the user I'm done.
Wow.
Yeah. And it doesn't have a terminal window open. So it asks a terminal environment server for a run CMD tool. It executes the code, verifies the fix, and completes the task. The bug is fixed.
That is amazing.
And the beauty of this iterative capability extension is what happens when things go wrong. It provides natural fault tolerance. Let's say in step 2, the edit file tool it retrieved threw a permission error or was the wrong kind of text editor.
Well, in a traditional RA system, the whole operation just crashes. The script fails, the user gets a red error message, and you have to start over.
Exactly. But with MCP-Zero, the AI simply assesses the failure message, refines its mathematical request, and asks for a different tool or a different server. It can self-correct on the fly because it is driving the process, not just following a rigid prefetch script.
I mean, a theoretical framework that can self-correct sounds incredible, but a theory is one thing. Does this active discovery actually work when scaled up to thousands of tools?
Well, to prove it, the researchers couldn't just use existing benchmarks. None of them were designed for this kind of hierarchical multi-domain tool discovery, so they had to build their own testing ground.
Right, I have the notes on that here. They created the MCP tools dataset, sourced directly from the official open source repository. We are talking about 308 distinct servers and 2,797 different tools.
It is a massive, realistic simulation of a full computer environment.
And the results they got from running evaluations on this dataset, using a benchmark called API Bank, are mind-blowing.
Show them the stats.
MCP-Zero achieved a staggering 98% reduction in token consumption compared to standard methods, a 98% drop.
We really need to contextualize what that means. A 98% reduction isn't just a minor efficiency tweak that makes a server run slightly cooler.
Right.
The difference between a complex task costing a developer $10 in API fees versus costing 20 cents. It fundamentally changes the economics of who gets to use autonomous agents and for what tasks.
And it achieved this massive cost reduction while maintaining, and in many cases actually improving, the accuracy of the AI across both single-turn and multi-turn conversations.
Yeah, that multi-turn aspect is huge. In the old system, when an AI is stuffed with 200,000 tokens of tool manuals, by the fourth or fifth back-and-forth message with a user, it starts to hallucinate or forget the original instructions.
Because its context window is just overflowing.
Its short-term memory is completely fried. But because MCP-Zero only holds the tools it is actively using at that exact moment, its working memory remains pristine. It can handle incredibly long, complex conversations without losing the thread.
They also ran this stress test called the needle in a haystack evaluation. They simulated an extreme condition where the AI had to find just one highly specific tool buried among all 2,797 tools in the dataset.
And what happened?
When they used standard context injection methods, as the tool count went up, the computational cost exploded exponentially. It was like a hockey stick graph of wasted money.
But with MCP-Zero, the token cost stayed completely flat, no matter how many thousands of tools were added to the pile. The search algorithm handled the load, not the AI's context window.
That is just incredible. Now, before we wrap up, I want to pivot to a fascinating detail buried in the paper's discussion section. It is a highly practical takeaway for anyone listening who uses AI daily.
Oh, the one-shot trick.
Yes. The researchers discovered a tiny trick that massively boosted the system's performance.
Right. This relies on a concept called in-context learning, or ICL. The researchers found that if they provided the AI with just one single example in its initial prompt of how to properly format a tool request.
Just one demonstration.
Yeah, just one example of what a good structured request looks like. The performance of models like Claude 3.5 Sonnet and Gemini 2.5 Flash shot up significantly.
But why does just one example make such a huge difference? I mean, why doesn't the AI just inherently know how to formulate a request if it's so smart?
Because language models are highly sensitive to what we call stylistic anchors. An AI is trained on everything from Shakespeare to Reddit threads to Python documentation. When you give it a task, it has to decide which persona or style to adopt.
Oh, that makes sense.
By showing the model exactly the tone and format expected, for example, showing it that it should request file system read, rather than writing a conversational paragraph saying, hey, could you please read this file for me? It immediately locks into the correct semantic space.
It grounds the AI's language so it aligns perfectly with the formal tool documentation. It's essentially a free, instant upgrade to the model's reliability.
Exactly.
And this relates directly to how you, the listener, prompt AI in your daily life. If you want an AI to write an email in a specific tone or format data into a specific table, don't just describe what you want. Give it exactly one perfect example of the output you expect.
That single stylistic anchor does more heavy lifting than paragraphs of instructions. It acts as a template that constrains the model's output in the best possible way.
Such a great tip. So, bringing this all together, what does the MCP-Zero framework actually mean for the future? If you rely on AI for your work, whether you are a software engineer, a data analyst, or just someone trying to automate your inbox, this shift from passive selection to active discovery is the future.
It really is. It means that the AI agents of tomorrow are going to be fundamentally different. Because they are operating with 98% fewer tokens, they will be vastly cheaper to run locally on your own hardware and significantly faster to respond.
But more importantly, they're going to be infinitely more capable of solving multi-step complex problems without you having to pre-plan their entire workflow.
Right, you won't have to be the project manager constantly handing them the right tools. You just give them a goal and they autonomously navigate the digital landscape, discovering and requesting the capabilities they need step by step.
Which leads to a rather profound implication for the future of software itself. I want to leave the listener with a thought to mull over. In the concluding sections, the paper briefly mentions a concept called ALITA.
Yeah, ALITA takes this entire concept one massive step further. It is a system that doesn't just actively find existing tools in a database. It actually writes raw code to create its own tools on the fly if it realizes the tool it needs doesn't exist yet.
Wait, really? It builds its own digital infrastructure?
Yes. So the thought I want to leave everyone with is this. If an AI framework like MCP-Zero allows an agent to actively search for exactly what it needs, and systems like Alita allow it to autonomously program the tools it can't find, well, are we moving away from the era where humans write software for AI?
And toward an era where AI builds its own customized, disposable digital infrastructure for every single question you ask it?
It's a wild thought.
We are moving from a static toolbox to a dynamic, self-assembling factory. It all comes back to John Dewey. We only think when we are confronted with a problem.
Exactly.
By stopping the practice of spoon-feeding our AI massive menus of answers and forcing it to actively confront the problem of its own limitations, we aren't just making it more efficient, we are finally teaching it how to truly think. Thank you for joining us on this deep dive. Take that idea with you, stay curious, and keep confronting those problems. We will see you next time.